Good afternoon. I am sorry that I'm unable to be at class today, but maybe doing a couple of problems like this in a video will work out for you. We're in section 10.4 on, I think the text just calls it applications, with using calculus to find maximum and minimum values in different settings. You might call it optimization applications. And let me say first of all that the textbook has some great examples that are worked out, and I would encourage you to look at those, try them, do them first, and then try the assigned problems on one or two of the assigned problems, which you'll find on the class website at rejoicealways.net. I have actually, on some of the problems that I assigned, pointed to one of the examples worked out in the text. So I'm going to do a couple here that I think are usually found to be helpful. The first one I'm going to work is problem 14 on page 744, and you'll find that I've assigned problem 13 in the calculus that you need to do on this one, as well as problem 11 will be similar to what I do right here. So let me put problem 14 from page 744 up, and we will work through it together. The main thing that gives my students problems on this is the algebra that is involved once you find your first derivative, setting that equal to 0. So that's what we'll concentrate most on here. Problem 14, we're on page 744. You're given a function, p of t is equal to 7.2t divided by t squared plus 36. We have a restricted domain. Excuse me, no we don't. Actually, we do have a restricted domain, but now this particular function, and you're going to see functions with really a different real-world application, but very similar in nature to this one on the problems that I've assigned. But this one is the proportion or percentage of people in a population that remember a candidate's name after T weeks into the campaign. So one thing that I would encourage you to do, like I have often on real-world application problems, is take this function and put it into your calculator to where you can evaluate P of t for different values of t, just to get a feel for the situation. I'm going to do that right now. Now I'm going to write this down. I will erase it because I'll need the room on the board to find the derivative in just a moment. But let me put a little chart up here. I'll pick some values of t, I'll put some values of p, and then I'll talk about what it is we're finding. And you need to have put this equation somewhere into your calculator so that you can do it. I haven't done that yet, so I'm going to right now, and I'll have 7.2 times, I'll use x when I'm putting it into my calculator instead of t, divided by, be sure you put the denominator in parentheses. I'm going to write it here. You know, when we write it on the board, it doesn't much matter, but on your calculator, you'll put 7.2 times x divided by, and then x squared plus 36, and then get past the parentheses and put plus 0.2. So there's my equation. I've got it entered. I'm going to evaluate this for some different values of t. Notice if you put 0 in for t, 0 times 7.2 is going to knock this term out, and so you just have 0.2. Now what this means is, before the campaign starts, or on the day the campaign starts, before you've done any advertising or anything, in other words, 0 weeks into the campaign, 0.2% of the population, or proportion of the population, 20% of the population recognize the candidate, or recognize his name. Okay? And I'm just curious, 1 week, 2 weeks, 5 weeks, 10 weeks, 20 weeks, 30 weeks, a year, 52 weeks after the campaign starts, what percent of the people will recognize this candidate's name? That's what this function is giving us. So I'm going to plug some values into my calculator and just evaluate it. If t is 1, and I evaluate the function, I get 0.3946, which means 39.46% of the people recognize the candidate's name 1 week into the campaign. So see, they're advertising on TV, and there's talk shows and things like that going on. And so we had 20% recognized when the campaign started, and we're already up to 39.46. See, if you're the candidate, and if the recognition is due to good reasons, that's a good thing. If everybody hates you, doesn't like your policies, I guess that wouldn't be very good. But we're assuming that this is recognize your name, and hopefully with favorable memories. I'm going to evaluate it for t equals 2. And if t is 2, I get 0.56. I'm going to go ahead and evaluate it for a few of these, and I'll write down the meaning of it. If t is 5 weeks into the campaign, I get 0.79, so 79% of the people recognize me. It's really 7902. 10 weeks into the campaign, 72.94% recognize. I guess I'll go write these down. 56%, 79.02%. Now I want you to notice something right here. 10 weeks into the campaign, I have fewer people recognizing the candidate's name than I did at 5 weeks. And so people are starting to forget. Now, the function doesn't tell us anything about why that would be so. Maybe there's other candidates, there's more names to remember. Maybe other issues are causing people to pay attention to those and not really remember the candidate's name. But, let's try 20 weeks into the campaign, and I get 0.5303, so 53% of people remember the candidate's name. 30 weeks into the campaign, I get 43.08, 0.4308 would be about 43%. 1 year after the campaign, how many people still recall the candidate's name? So we'll evaluate it for t equals 52. And I get 33.66%, 0.3366. So 33.66. We're down to fewer than the first week of the campaign. Still more than what people originally recognized when the campaign started. Now, I don't know that this is all that accurate, a real-world function to measure candidate name recognition or not, but it's certainly a good, suitable example for us to try. Now, here's what we are interested in knowing. How far into the campaign will I have the maximum number of people recognizing my candidate's name? And we can look right here. 5 weeks into the campaign, it was 79%. We might also want to know not only how far into the campaign will that number be maximized, but what will be the maximum number of people that recognize my candidate's name. What percentage? I've got 79.02 here. Will it be higher than that or lower? Could that be the maximum? And how far into the campaign will that occur? Those are the things that I'd like to know. That's an optimization problem, is finding a maximum or a minimum. Now, if I disregard everything to do with understanding the function, although this is a great idea, I would recommend you do something like this on every single problem. Figure out what your function is. Sometimes it'll be given to you. Sometimes you're going to have to figure it out, and I'll show you one like that from our next example. Evaluate the function at different values of your variable, and make sure you have a good mental understanding of what's going on. That'll help you to recognize if the answer you get makes sense or not. So I'm going to erase my chart here. You've got it on the video. If you want to replay it, look at it, take a screen print or something of it, you certainly could. But just go back to our calculus now. How do you find the maximum minimum values for any function? Well, we're going to take the derivative, first derivative. And here I have a quotient. T is my variable. I have a quotient. We have to use the quotient rule. And so I don't know if you recall or not, but if I have a function y is equal to f over g, then the quotient rule says that y prime, the derivative, is going to be f prime times g minus g prime times f over g squared. Now, I'm awfully short on board space here that I can get into the video camera, the picture. And so you might need to write that down on your notes while you're doing this problem or one like it and have it. I'm going to erase that, but that's what I'm going to use right here, the quotient rule to take the derivative of this. And you can always pause this video at any time and write down anything you need to write down. So if I identify the numerator here, the top part is being my f, and the denominator is being my g, then f prime, I'm going to scoot this down a little bit. F prime would be 7.2 times my denominator, minus g prime would be the derivative of t squared plus 36 would be 2t times f over g squared. So there's my derivative. I need to simplify this a little because I'm going to end up setting this equal to 0 and solving to find critical points, points that are potential maximums or minimums. And so I'm gonna simplify this a little bit. Now, there's two things you can do. I can multiply the 7.2 here times everything here, and then combine all my like terms. But there's an easier way. And what I'm going to do is I'm going to factor 7.2 out of this term and out of this term. That would give me this. Of course, when I factor 7.2 out of this first term, you see how I get the t squared plus 36. Right here, if I factor 7.2 out, I still have a 2 times t, and that's where the 2t squared came from. And that's all over my denominator. And now I'm going to go ahead and combine my terms inside the brackets here. T squared minus 2t squared is going to be negative t squared. I'm going to have 36 minus 1t squared. And I'm going to erase my top function up here. Put that down. Again, I'm limited on board space. So I have my 7.2 times t squared minus 2t squared would be a negative t squared. I'm going to write it like this. 36 minus t squared over t squared plus 36 squared. Now there's a reason why I chose to write it that way, which will become apparent when I set this equal to 0 and solve to find critical points. Again, you can replay and get a screen print or write down any part of this that you need to. I'm going to set this equal to 0 now. I'm going to find my critical points. I'm going to set my equation equal to 0. Now, you really can get critical points two ways. Any place where your first derivative is equal to 0, of course, gives you a critical point. Any place where the denominator is 0, this thing would be undefined, this expression would be undefined, and you'd also have a 0. But if I look at that denominator, no matter what I let t equal, I'm squaring it, so it's going to be the smallest thing 0 or some positive number. I'm going to add that to 36, I'm going to square it. This denominator is never going to be equal to 0. So I have a fraction is equal to 0. I have a denominator that can never equal 0. So the only way this fraction can equal 0 is if the numerator is equal to 0. So I can ignore the denominator, and solving the original equation I had is the same thing. It's just setting the numerator equal to 0 and finding the solution for that. Textbook way to find this, there's really a couple, but we can factor that 36 minus t squared is the difference of two perfect squares. So that would be 7.2 times 6 plus t and 6 minus t. So I get critical points of t equals negative 6 or positive 6. If t is negative 6, 6 plus negative 6 would make this factor equal to 0, and make the whole expression equal to 0 and be a solution. If t is positive 6, it makes this expression, this factor, equal to 0. If this factor is 0, no matter what the rest of the factors are, 0 times anything is going to be 0, and that is the solution. So these are my critical points. T equals negative 6 or positive 6. So that's where I have potential maximums or minimums for this function. Now, what does T represent? Well, in the real world, it's how many weeks into the campaign. So -6, this is an analytic answer, but it's not in the domain. Up here, the domain of our function T has to be greater than or equal to 0. So essentially, we can throw that out. One thing I do need to do is, I know that 6 is going to be an interesting critical point. I'm going to go ahead and do a first derivative test to make sure that this is what I'm trying to find is a maximum. I want to know is that a maximum value or not, 6 weeks into the campaign. And so I'll do my sign graph test, or I'll construct a sign graph to apply the first derivative test. I'll take a number in each region of my number line chart for T, and that'll tell me if in that region if P prime is positive or negative, and that will tell me if P is increasing or decreasing. We've done all this before. This should be old hat to you. If I take a number in this far positive region, and again, some of y'all don't like the way that I do this, but you can always take a number like 7, evaluate it in this function, and see if you get a positive or negative number. But you really don't need to do any arithmetic. If I take 100, 100 squared plus 36 squared, that's going to be a positive number in the denominator. 100 squared is going to be really big. 36 minus that, this is going to be a negative number. Times a positive, times a positive. My derivative is going to be negative for any t greater than 6. If I take a number in this region, like t equals 0, that's 7.2 times 36 over 36 squared, positive, positive, positive. Everything's going to be positive. We don't care about this region. Anything to the left of -6, we don't care. So you can just essentially forget about that. Right here, if P prime is positive for all numbers in this region, then P is increasing. If P prime is negative here, it's decreasing. So you have a function that is increasing and then decreasing. When T is equal to 6, you have a maximum, a relative maximum value. Now, that tells us that in 6 weeks, we have maximum candidate name recognition. What % of the people recognize the candidate? And so we need to evaluate P of 6. I need to find the y-coordinate right here, P of 6. So I'm gonna dispense with my derivative now. I don't need it for the rest of the problem. I'm going to evaluate P of 6, and I could plug it in, right here. Just use a calculator, but remember before, I encourage you to put this function into your calculator so that you can evaluate it for different values of T. And so I'm going to go back to my calculator where I did that, and I hope you did the same thing. I'm going to evaluate that function when T is 6, or when X is 6. And I get 0.8. And that means therefore, 80% recognize the name. So, what I have determined is the maximum percentage of the population in this campaign who will recognize my candidate's name, if this is an accurate function, is 80% of the population, and that's very good. When will that happen? 6 weeks into the campaign. So that's the practical information that we have obtained, and a good example of using calculus to get it. And the functions that you'll do on problems 13 and 11 will be real similar to the algebra, to the way that I handled this problem right here. If you can't figure it out yourself, then you need to take, for problems 11 and 13, and you need to go to the math lab, and you need to get with your tutor or a study buddy. And so you can get help with the algebra involved after you found P prime, in simplifying it, setting it equal to 0 to find your critical points. Okay, I'm going to end this video, and we'll do another problem in just a second.